An electroscope and a pair of metal spheres will be used to demonstrate electrostatic induction. If one of the spheres is charged, the sphere can cause the electroscope to deflect. Now we'll start with both spheres neutral. The spheres are placed in contact with one another. The negatively charged rod is brought near, but not touching, one of the spheres. The spheres are separated, and the rod is removed. When one of the spheres is touched to the electroscope, the scope deflects. What will happen if we touch the other sphere to the electroscope as well? The electroscope goes back to zero. The charges induced on the two spheres are equal and opposite. This animation shows how the charges develop on the two spheres as the charged rod is brought near.
This aluminum rod is placed on a bearing stand so that it is free to rotate. A plastic rod is positively charged by rubbing it with a piece of wool. When the plastic rod is held near the neutral metal rod, the rod is attracted and swings toward the plastic. We'll repeat that with a rubber rod, which develops a negative charge when rubbed with wool. The negatively charged rubber rod also attracts the neutral metal rod. This animation shows how the free charges in the metal rod are attracted or repelled by the two rods. This separation of charge inside the metal causes the aluminum rod to be attracted to a charged rod of either polarity.
Here's a device called an electrophorus, which generates electric charge in an interesting way. It consists of an acrylic sheet and a round metal plate attached to an insulating arm. If we rub the acrylic with a wool cloth, the acrylic acquires a positive charge. The metal plate is then placed on the acrylic. A grounded wire is then touched to the metal plate. If the plate is now lifted off the acrylic and brought up to a second metal plate that is grounded, a spark jumps between the plates. If we repeat the procedure without recharging the acrylic sheet, we can get another spark. And another. How can we continuously generate charge without recharging the acrylic? The electrophorus works by electrostatic induction. When the neutral metal plate is lowered onto the positively charged acrylic, the negative charges in the metal are pulled to the bottom of the plate. That leaves a net positive charge on the top surface of the plate. When the top surface is connected to ground, electrons conducted from the ground neutralize the upper surface. The plate now has a net negative charge. The positive charge is still on the acrylic, so the cycle can be repeated. Electrostatic generators, such as this Wimshurst machine, use electrostatic induction to separate positive and negative charges and can create very high voltages. Here's an animation of a very simple type of electrostatic generator known as a voltage doubler. An acrylic disc with small pieces of metal foil near its outer edge is mounted so that it can rotate when turned by a crank. Two metal shells are wrapped around the edges of the disc. A metal bar with conductive brushes at either end contacts two of the foil pieces at the positions shown. Assume the two metal shells start out with a small imbalance of charge, so that one is more positive than the other. That charge imbalance induces charges on the two foil pieces, which are in contact with the brushes. When the disc rotates, these foil pieces break contact with the brushes, each coming away with a small charge that is opposite that of the metal shell on that side. Each foil piece that follows comes away with the same charge. When these charged foil pieces reach the center of the opposite shell, they contact a conductive brush inside the shell and surrender their charges to that shell. As charge builds up on the shells, the process of induction becomes stronger, leaving more charge on each of the foil pieces and accelerating the charging process. If discharge rods are attached to the shells, a spark will pass between them, reducing their charges and starting the cycle again. Here's an interesting device known as a Kelvin water dropper that generates static electricity from the energy in falling drops of water. Water is allowed to fall from these two droppers through metal rings and into the metal cans below. After a few seconds, enough voltage develops between the cans to flash a small neon bulb. This animation shows how the generator works. Assume a small charge imbalance initially exists between the cans. The can which is more positive is connected to this ring, and the positive charge on the ring attracts negative charges into the droplet at the end of the dropper. The droplet breaks away, carrying the negative charge down into the negatively charged can below and increasing the charge on the can. On the other side, positively charged droplets fall into the positively charged can. The charges on the two cans increase until the voltage is high enough to flash the neon lamp. This wood bar is placed on a stand so that it is free to rotate. When a positively charged plastic rod is brought near, the wood is attracted and follows the rod. Repeating this demonstration with a negatively charged rubber rod shows the same effect. This Van de Graaff generator can be used to develop very high voltages. This animation shows how the generator works. A rubber belt passes over a pair of rollers with the bottom roller driven by a motor. The upper roller is contained inside a smooth, hollow metal sphere. A high-voltage DC source is connected to a metal comb positioned near the bottom roller. It transfers charge to the moving belt by corona discharge. When the belt enters the hollow sphere, it passes by another metal comb which is electrically connected to the sphere. The charge is pulled off the belt by the comb and moves to the outside of the sphere. Since the electric field inside the charged sphere is nearly zero, the comb can continue to remove charge even after there is a large amount of charge on the sphere. The voltage on the outside of the sphere continues to increase until it reaches the breakdown voltage of the surrounding air. We'll show the shape of the electric field around this Van de Graaff machine using these paper streamers. When the machine is turned on, the sphere and the streamers become charged. Electrostatic forces push the streamers away until they follow the electric field lines of the sphere. A person standing on an insulated platform with their hand on the machine shows a similar effect.
We'll use this Van de Graaff high-voltage generator and a grounded metal wand to illustrate how electrical discharge differs between sharp and blunt objects. When the Van de Graaff generator is turned on, paper streamers fan out and follow the shape of the electric field around the sphere. The wand is grounded. When its blunt end is brought near the sphere, there is little effect on the streamers until a large spark passes to the wand. The streamers collapse momentarily, but quickly rise back up until the next spark. When the pointed end of the wand is brought near, the streamers collapse and stay down. The sharp point drains the charge off the sphere without visible sparks.
We'll use this apparatus to show the electric field configuration around various charged objects. Particles suspended in the fluid inside this chamber will line up in the presence of an external electric field. The alignment shows the lines of the electric field. If we put this small metal cylinder on top of the chamber and charge it using this pistol, This is the shape of the electric field from the metal cylinder. Here is the electric field between a pair of parallel metal plates, one of which is positive and the other negative. Here is the field between two oppositely charged circular conductors. Notice the absence of an electric field inside the inner conductor. We'll use this model house and a high-voltage electrostatic generator to demonstrate how a lightning rod works. One side of the generator is connected to a metal ball inside the chimney. This sharp rod is also electrically connected to the same side of the generator. The other end of the generator is hooked to this copper sphere, which simulates a charged cloud in the atmosphere. When the generator is cranked with the lightning rod down, large bolts strike the chimney. When the lightning rod is raised, the bolts stop. When the lightning rod is lowered, the large bolts resume.
We'll place this pinwheel on top of a Van de Graaff generator and turn it on. The high voltage from the generator causes corona discharge from the points of the pinwheel. The discharge ionizes nearby air, then repels it strongly from the point, making the wheel spin. Electrostatic precipitators are often used to remove pollutants from industrial smoke before it reaches the atmosphere. To demonstrate the effect, we'll use this acrylic tube with a metal conductor at each end, connected to an electrostatic generator. Smoke is put into the chamber with each of the conductors hooked up to one end of the generator. The high voltage that is generated sweeps the smoke particles out of the tube.
Like all particles, electrons in motion have momentum. We'll use this discharge tube to demonstrate that fact. The tube is evacuated with an electrode at either end and a glass wheel with mica paddles, which is free to roll along the wheel. If we turn up this high-voltage power source and send a beam of electrons through the tube, electrons striking the paddles of the wheel roll it along the tube. When we reverse the direction of the voltage, the wheel reverses direction.
This iron wire in series with this small lamp will be used to demonstrate the effect of heating on resistance. A current is sent through the wire and the bulb, which lights brightly. When a gas flame is lit beneath the wire, current through the wire drops and the bulb dims.
This coil of copper wire in series with this lamp will be used to show the effect of cooling on electrical resistance. We'll run a small current through the coil and the lamp, which lights dimly. When the coil is cooled by dipping it into liquid nitrogen, the brightness of the bulb increases dramatically.
Here are 3 light bulbs. We'll hook the first bulb up to house current, then hook the other 2 bulbs in parallel to the first, one at a time. The brightness of the bulb stays constant as each is hooked in. Now we'll again hook up the first bulb, then hook the other two bulbs in series with it, one by one. How will the brightness of the bulbs change? The bulbs dim as each new bulb is added. Have you ever seen your house lights dim when you turned on a heater or heavy appliance? We'll use this model of house wiring to demonstrate the effect. Two resistance wires will substitute for the normal copper wires used in a house to increase the effect. They run ordinary household current into this bank of lamps and heaters, which can be switched on and off individually. We'll first switch on the lamps. Then heaters will be switched on one at a time. When enough heaters are added to the line, the lamps dim. The electrical energy lost in the wires which deliver the current is dissipated as heat.
When a current flows through a wire, heat is generated. We'll use these two different wires hooked in series to show how the amount of heat generated depends on the resistance of the wire. This wire is made of copper, a low resistivity metal, while this wire is made of nichrome, a metal with a relatively high resistivity. We'll put a paper rider on each wire, then run the same current through both wires to see which heats up the most. The nichrome wire burns its rider almost immediately, but the rider on the copper wire isn't even scorched. We'll skewer this hot dog onto two nails and run a current through it to show the heating produced by the current. 110 volts are applied to the nails, and a current begins to flow through the hot dog. After a few minutes, the hot dog begins to steam from the heat produced by the current. Here is a circuit used to rectify alternating current and transform it into direct current. We'll look at the different components of the rectifier circuit to see what part each plays in the operation. This transformer puts out alternating current at 6 volts. We can see the waveform of the current by attaching the output terminals of the transformer to this oscilloscope. This alternating current feeds into a diamond-shaped bridge of 4 diodes. Here is the resulting voltage across one of the diodes. At the right and left corners of the diamond, the voltages from the individual diodes add together to produce this waveform. This pulsating current is then filtered by 2 low-pass filter stages. When the filter stages are connected one by one, the output flattens into a clean DC voltage. This transistor amplifier circuit will be used to show the properties of transistors. This leg of the circuit provides the signal, a current which can be varied by turning a potentiometer. This signal feeds into the base of the transistor. The collector to emitter voltage is supplied by this set of batteries and is controlled by turning this potentiometer. Here is the input signal, the current flowing into the base of the transistor. Here is the output of the transistor, the current flowing between the collector and the emitter. The output is an amplified version of the input. We can change the amplification by increasing the collector to emitter voltage.
This light bulb is wired in series with these two metal prongs, so that if something conductive touches the prongs, current can flow through the bulb. We'll use this setup to demonstrate the conductivity of different solutions. Here is distilled water. Here is distilled water with salt added. Here is distilled water with sugar added. Here is distilled water with vinegar added. Finally, here is ordinary tap water. When an electrical current is passed through water to which a small amount of acid has been added, the water splits up into its component gases, hydrogen and oxygen. This glass tube has two electrodes, each in a separate leg, so that the gases may be collected from each electrode separately. When we run a current through the water, gases build up in the tubes in a volume ratio of 2 to 1. If the larger of the two volumes of gas is released near a lit match, it burns with a pale blue flame.
Electroplated objects are a common part of our everyday lives, such as this chrome-plated car bumper. We'll use this tank filled with a solution of copper sulfate and 2 electrodes to show how it's done. A current supply is hooked up to the electrodes, one of which is copper and the other carbon, and they are placed in the copper sulfate solution. When a current is run through the solution with the copper electrode positive, a plating of copper builds up on the carbon electrode. This animation shows how the positively charged copper ions in the solution are attracted to the negatively charged carbon plate, where they bond to the surface. This parallel plate capacitor and an acrylic sheet will be used to demonstrate the force on a dielectric between the plates of a capacitor. The sheet is attached to the end of a balance arm so that it is free to swing up and down. We'll place it between the plates of the capacitor and charge the capacitor to a high voltage using this electrostatic generator. When the capacitor is charged, the force on the dielectric pulls it down between the plates. This animation shows how the polarized molecules of the dielectric are reoriented by the electric field of the plates. This new orientation results in an attractive force on the dielectric, which pulls it down between the plates.
We'll assemble a simple capacitor out of these 3 components. This high-voltage electrostatic generator will be used to charge the capacitor. A wire is connected from one side of the generator to the outer metal shell of the capacitor, while a loose chain connects the other side of the generator to the inner conductor of the capacitor. Let's charge the capacitor. Now that the capacitor is fully charged, we can disconnect it from the generator and use this discharge rod to demonstrate the high voltage which exists between the 2 metal plates. We'll now repeat the charging. But after the capacitor is fully charged and has been disconnected, we will disassemble it into separate parts. If we now touch the discharge rod to the two metal plates, there is no spark. What has happened to the charge on the plates?